Hello everyone, welcome to Understanding Physics, in which I'll try to guide you through understanding physics. So today on General Physics 2, we want to talk about the interference as well as the diffraction, two of the properties which comes from the property of light as a wave. So previously we have talked about geometrical optics, in which we assume light rays are lines, but in here we will also discuss about the light as waves, so that they have constructive and destructive interference. So before we get started, please consider subscribing as well as liking the video, and also please check the notes in the description for the notes throughout this entire discussion. So let's start to talk about something which you call as the coherence, as well as later on the interference. So what coherence exactly means is that a coherent light is where the wave is periodic and it is well maintained. So it is uniform throughout the entire length of the ray. So something like this isn't truly coherent because the property of the wave is only at the section. But if you have the wave to be constant over the entire length, you call that light to be coherent. And technically, you don't really have a truly coherent light. Instead, you could have light which is coherent over a certain length, which you call as the coherence length. Now, the importance of knowing coherence is that this will later factor in when we talk about the interference. So we need to produce these coherent light for us to analyze. And what is a better coherent light other than the laser? So a laser pretty much produces a coherent light. It is well defined over one particular direction, and it is coherent over a very long range. So it doesn't truly die out the further you go. It's a very uniform, even though if you change the direction. So throughout this entire discussion, we'll be talking about coherent light. Now, for this monochromatic light, there are certain properties when you are talking about waves, which is the constructive interference as well as destructive interference. So let's give some examples. So if I have waves like this, and then I produce another wave which goes like this, you could see that there is a phase difference from here to here to be about lambda over 2, or pretty much the wavelength divided by 2. Now, because of this shift of lambda over 2, this means that you are shifting the phase by 180 degrees. So what you have here is something like cosine x plus the cosine of x plus pi. Now, if you try to do the computation, so we could just expand this, cosine x plus cosine x cosine phi minus cosine x the sine x sine phi. You would have this component here to be 0, and what you would have left here is this negative cosine x, which will be 0. So what we see here is that if you have a 180 degrees phase difference, you would have destructive interference, in which at every single point throughout this entire ray, the rays will destroy each other out to produce no intensity or 0. So this is something interesting, and this is because you could actually do this with multiples of 360 degrees. So pretty much this works for m lambda over 2, in which m is odd. So if you have any type of phase difference which is multiples of the half wavelength, which is odd as well, you would have destructive interference. But what about if you have it to, let's say, to be displaced by a certain value called pi? So if I draw this again in here, so in here there's a change in the wavelength here. So from this peak towards this peak, that's lambda, right? And so with the wavelength of lambda shift, it will be 360-degree phase difference. And so this is like cosine x plus cosine x to plus 2 pi. What you would get here is it's going to be 2 cosine x. So you can see here that the amplitude is much more greater compared that to before. And this is what you call as constructive interference. So it produces a higher amplitude compared to the original light. So if you have two lasers and then you put them together within the same wavelength, within the same phase but differing by a number of wavelength, it will be constructively interfering. But if it is multiples of the half wavelength, it will be destructively interfering. So this works for any multiple of lambda. So these two are the main characteristics when we are talking about constructive as well as destructive interference. So after we have already talked about this property of interference, we can now start to talk about the idea of the double-slit experiment. So the double-slit experiment shows you that certain stuff are wave or particles. So the way that we'll do this is that if you shine light very far away, so that it will be like a wavefront like this, and then it will hit these points in which you cut a slit into it so that the light could pass through, but this is very small, and the distance between these two are called d. And the distance from this to your screen is going to be big D. So a property that you need to remember when you're talking about waves is that for any single part of the wave, it becomes a point source in itself. So this is going to be a point source that will radiate outwards. Same thing with this point. It's going to be a point source radiating outwards. So if you are interested in, let's say, one particular point here, let's say here, within a distance, let's say y, the question is it light or is it dark? So we could actually observe this first by actually figuring out where's the bright fringes and where's the dark fringes. So the bright fringes is pretty much where it is constructively interfering. That means that you need to have the phase difference or pretty much the phase difference in the length to be m lambda. And so where is the phase difference within your double-slit experiment? So if you look at these 2 points and then take a very long line towards a particular point, you would have this angle to be theta, which means if you take this line here, this would also be theta. So as long as the screen is very far away, you could figure out that there is this change of length here in which this angle here is theta, even though it's not exactly true. But anyways, if we have this small length here to be the phase, or you could use some trigonometry to figure out that this is d sine theta, this will be your criteria for bright fringes. You could use the same logic for dark fringes. It's m plus half lambda equals to d sine theta. So the m here is any integer z, and it will work. But technically it's a positive integer, so it's technically the natural number. So with only the idea of figuring out where is the bright fringe and the dark fringe is pretty useful when you're trying to describe how wide is the slit, because you could figure out what's the length here. But if you're talking about the relative intensities, you need to use a little bit more mathematics behind it. So let's discuss much more about this. So we will just state that the electric field is gonna be sine omega t. So from the first point here, on this point it's gonna be E sine omega t, but on the other one it's gonna be E sine omega t plus phi. So in here I introduce a phase difference. So anyways, this is Ep anyways. Let's just write that. So remember that waves could be added up straight away. So we could just add them both straight away. So we would obtain Ep sine omega t plus sine omega t plus phi. Now, there is a property of sines and cosines, which I'll just write here. Sine alpha plus sine beta is the same thing as 2 sine alpha plus beta over 2. Multiply this by cosine alpha minus beta over 2. So if we do this, it's going to be 2 Ep sine omega t plus phi over 2, and then the cosine of negative phi over 2, which is also phi over 2. Now, this property here depends on time, so you could take the average anyways. But in the end, what really matters is the amplitude, or the 2 Ep cosine phi over 2. So now the question is, what is phi? We don't really define it straight away. So the way that I'll try to describe about the phase is by using a little bit of wave theory. So if you have a certain displacement here, which you call that as phi, it is related to the fraction of displacement. So in here, your displacement here is already figured out to be d sine theta. So it's d sine theta, and then you compare this with the length of the entire wavelength, and that's lambda. So that's the fraction of how much did you move. But when you're talking about waves, it's much more convenient if you express this in the form of radians. So this is in cycles. So what you could do is that you could transform this into radians just by multiplying it by 2 pi radian. So you would get 2 pi d sine theta over lambda. Now, if you have the theta to be, so now if you have the d to be far smaller, compare that to d, to the very big D, what you could have here is that this is very similar to, so if we draw this here, the sine theta is going to correspond to, that's D, and then this is the position in terms of Y. So what you would have here, oh sorry, so this should be Y, far less than D. It's going to be 2 pi yd over lambda big D. And this is your phase difference. So you could just put it into your formula straight away. So you would get 2 EP cosine pi yd over lambda D. So y is the position of where you are interested in. And so you could figure out what is the intensity just by squaring it. So the S bar, or the average intensity, is going to be 4 EP squared, or it's going to be just the initial intensity. Multiply this by cosine squared pi d over lambda dy. So technically, the way that you could actually transform from this electric field into S is by using the E cross B over 2 mu 0, I believe. Yeah. But then it's much more simpler if you just square it, and then you can take the EP here and then turn it into S0, because the intensity is pretty much so the intensity is pretty much proportional to the square of the electric field. So that's why we use such notation straight away. So we get this. And with this, you could actually figure out what is the wavelength of your, laser, or maybe even the distance of the slit if you know what the other variables are. So we have talked about this entire format, but let's talk about multi-slit interference pattern. So we could actually consider of trying to figure out what's the maximum value of your multi-slit system. So let's assume if we have 3 slits, they have the same phase. So remember when we talked about phase for 2 slits, it's m lambda equals to d sine theta. But maybe if we try to add another slit, we need to make sure that it is also in the same phase. So if we have only 2 slits and then we fulfill the m lambda equals d sine theta, that means that if you compare these other 2 slits, it's also going to be m lambda d sine theta, which means that this entire thing still holds for the maximum. But there are also certain conditions in which you could have it to be destructive. You could see here that the amplitude will be 0. And this is the phase in between each of these, which is m over n lambda equals to d sine theta. So the easy way to explain this is that if you have your phase here to be a fraction of the wavelength, let's say 1/3 of the wavelength, it's going to be going this way, and then there's a change 60 degrees, and then there's another change from this angle to this angle here to be 60 degrees, going back to the initial condition. Sorry, it should be 120 degrees. So you could see from here that with this condition, you would have destructive interference. Thus, this guy has minimum or dark fringes. So this is a relation that is very useful for you to remember, is that if you have your d sine theta to be multiples of your lambda, it's going to be constructive, while if you have fractions of it, it's going to be destructive. Now, because of this, you could actually see a fact that if you have 2 slits, it's going to be something like this. But if you have 3 slits, you would have a maxima, and then after that, there are 2 dark fringes. So 1, 2. And then it will go back to the big one. So this is when it's 0, this is 1/3, this is 2/3, and this is 1. So you could see that there is these 2 major maximums, and then there's this one small peak. And if you count the number of these large peaks, there is only 2. Every single time there's only 2. But the number in between of these large peaks is only n minus 2, where n is the number of slits. So with this, you could actually figure out how many slits does your multi-slit does this multi-slit partition that you have. But maybe you could actually extend this towards much more higher orders. So this is what you call as a diffraction grating. It is when your n goes to infinity, or it's pretty much very large. And so if you have these very large diffraction grating, instead what you would have is you would have peaks after peaks. And so these peaks will only depend. So m lambda equals to a sine theta. Oh, sorry, it's not a sine theta, it's d sine theta, or the distance between the slits. So this will be the maxima. It's always like this. So using a diffraction grating here, you could create very large peaks, and then there's a plateau of 0. So it's something like this. So it's not really periodic in terms of like a sinusoidal, but it's much more concentrated. And this is very useful when you're trying to figure out what's the wavelength of your light. You could use diffraction grating for you to determine what is the wavelength of the light. So let's actually do this problem. Let's say if you have this one peak, and then there's another peak here, in which they both correspond to different wavelengths, because as you know, m lambda is the sine theta, and the sine theta here is d lambda, so the sine theta was, let's see, sine theta was y over d. So we could express this as y over d. Now, if you know this value, and you want to know what this value is, and m is a arbitrary constant that's pretty much labeling your peaks, you could actually use the position of y to figure out your lambda. So the lambda is linearly dependent on the position of the peaks. So this is a way for you to differentiate between certain wavelengths, and you could compute this. But let's say if you have, so if we try to refer towards the next minimum point after this peak, it's going to be mn plus 1 over n, in which n is the number of slits and then lambda is the order. And then you would have another one which has the same d, which means that you have the same system, and then the sine theta min of your new wavelength is going to be mn plus 1 over n lambda prime, or lambda prime is your new wavelength. So you would have two different wavelengths hitting this diffraction grating, and you want to figure out what type of light, so what's the picture of the light. So with this, what you could do is that if you actually try to, so in order to differentiate both of these wavelengths, you need to remember that there is light interference. So if you have the first peak to be here, and then you have your other peak here to be here, what might end up is that with the superposition principle, it will be something like this. And so you need to figure out if you could actually see the differences between the peaks. And this is the most important thing. So this is where we will introduce the idea of resolving power. So the idea of resolving power is that if you take the max here and then it will be going to the next min, that means that the next component here would be at its pure composition. So if we actually consider for our new particle, for the new wavelength to have its maximum at the particular point, it's going to be m lambda prime, right? So if we want to have this theta prime max to be equal to the theta minimum, or to have this to have only one of the peaks to be the one that is contributing towards your entire diffraction pattern, interference pattern, you would need to make an equality between this guy and this guy. So what you would have here is mn plus 1 over n equals to m lambda prime. So this will produce your m plus 1 over n lambda equals to m lambda prime. Or you could solve this again. So the m lambda prime minus lambda is equal to lambda over n. So with this, we could actually re-express everything. Lambda over delta lambda, which is the small change in your lambda, will be nm. And this is what you call as resolving power. Resolving power. So what this actually gives you is that if you have a diffraction grating with n amount of slits, you could read off the nth position and to figure out if there is any other light composition within your original light, because it might seem that it is only one color if you only use a single slit, but instead, if you use a diffraction grating, you could see that there are technically two different peaks corresponding to two different wavelengths. So that's one use of this. So maybe a very clear example of this is that if you actually look at the stars, you might see that there are two stars near each other, and and then you couldn't really determine which star is which. So you could actually use a diffraction grating just to actually to get two different wavelengths, which means that it will correspond to which corresponds to two different stars. Another type of diffraction is something which you call as the X-ray diffraction. So let's try to get this intuition. So if you have your atom to be a crystal in which they have their own planes, and then you hit this with X-ray, what's going to happen is that there will be an interference pattern or a diffraction pattern, or something which you call as an X-ray diffraction anyways. So the condition in which it will later have constructive interference is that if this excess length here corresponds to a constructive phase difference. So m lambda should be, so in here I will take this to be your theta. Sorry, this one is our theta, which means we could determine that this is also our theta. That means this should be 2d sine theta. This condition must be, this is the condition where there's constructive interference. So if you change the diffraction, sorry, if you change the angle of your X-ray, you could determine what is the length between these two. No, sorry, you could figure out the distance between the two planes. And this is very useful when you're doing crystallography. So you could determine what is the shape of the crystal based on the peaks, and then you could also determine what is the interatomic spacing. So there are multiple other gratings that you could use to do interference pattern, but this is the most general cases. So we have already talked mostly about interference, right? And so in here I want to introduce the idea of interferometry. So interferometry is pretty much any type of method for you to create such interference pattern, or pretty much phase changes for your light. So in here I will give some examples of such things. So I will introduce the idea of reflection when it comes to different refractive index. So if you have, let's say these two boundaries here, and then if you have light going through something like this, and this is what you call as N1, and this is N2. This will be N1 again. So if N2 is far greater than N1, the reflected light will be having a phase change of 180 degrees. But if you have the light entering here towards N1, the reflected light will have the same phase. So this will be 0 degrees. So this is just a fact that I will just tell to you straight away, because trying to prove such phase difference requires much more advanced physics that I won't fully discuss in here. But maybe future on I might discuss a little bit about why there are phase changes throughout the boundaries of your refractive index. So just by using this, if you know the distance between this guy and this guy to be d, let's say, so you could have a constructive interference at this boundary here when the condition exists. So what's the condition? So the condition will be 2d. So 2d will be double distance here, so it goes this way and then going back, must to equal to m plus half lambda n. So lambda n is pretty much the frequency within your refractive material, and this m plus half is pretty much comes from the constructive interference. But this constructive interference is already due to 180 degree phase change. So there is a phase change first of the reflected light, and then the transmitted light will reflect back and then we'll produce the same frequency again. So we just need to figure out the opposite. Instead, what we consider is the 180-degree phase change, which is something which we have already plugged in when we put in n plus half lambda n. So remembering about what lambda n is the lambda over n. This is the original wavelength, and this is your refractive index. So you could just substitute everything in order to get 2nd equals to m plus half lambda. So with this, you could actually figure out the refractive index for particular wavelengths, and also you could actually determine the wavelength if you know the refractive index. So it's a very useful information that you could use from interferometry. Another type of interferometer is the Michelson interferometer. So the Michelson interferometer pretty much has laser, and then you split it into two. You would have this one and this one, and they will reflect back. Now, if there are certain changes within this length here, so if they have the same length, it's gonna be constructively interfering. But if it has some changes, you could observe some destructive interference when you have these changes of your length. Now using this, you could actually gain very useful information about the entire universe, because it turns out that if you actually change the spacing by a little bit, you would have this interference pattern, and because of the change of the position means that you could actually detect objects very far away if they have certain gravitational field. So this is something that I won't fully discuss now, because later on we will discuss about relativity, in which if you actually talk about general relativity, you would know that gravity affects space-time. And so later you could detect the space-time by using such Michelson interferometer. So if you put this guy to be lengths of a very large scale, maybe kilometers, you could detect very small changes. So it's a very useful tool just to determine if your space is changing or not. So I want to introduce about the Huygens principle, in which it will later lead us towards diffraction. So the Huygens principle is the principle in which the wavefront behaves as point source. So if it goes like this, that means that there are point sources everywhere. So what does this has to do with diffraction? So if we put, let's say, if we send light in towards a slit in which we know the length here to be A, we could express this as multiple very small point sources, or like multi-slit interference pattern. So this will be m over n lambda equals to d sine theta, in which this is corresponding to the dark places, or your dark fringes, destructive interference. Now, what d here is going to be a over n. So what you get is m lambda equals to a sine theta. And this is where all of your dark fringes are located at. So you could also do this in a much more mathematical way, and this will later result in the pattern of the diffraction pattern of sine c, or the complementary sine function. So the way that we'll derive this is by actually figuring out what the phase difference is. So if we have the y-axis here to be 0, and then we're going up, what you would have is that you would have phase difference to be equal to So if we draw this here, this will be y, and this will be thetas. So what you would have here is gonna be 2 pi over lambda, which is the wavelength or the total length. Multiply this by y sine theta. And each of these points will have the electric field to be EP divided this by A, so it's pretty much distributed. Multiply this by dy, so it's a very small length over the area, which will give you the proportions. You multiply this by the sine omega t plus phi. Now, what you need to do after this is that you just need to do the integral. So doing the integral might seem challenging because there's function inside the function, but it's actually pretty simple if you know certain tricks about it. So if you take the integral of the electric field, or the sums pretty much from 0 to A, what you would obtain, it's going to be EP over A, the integral of negative cosine omega t plus the phi, which is 2 pi lambda sine theta y. You divide this by 2 pi over lambda sine theta. Evaluate that from 0 to A. So plugging the values in, what you would get this to be EP over, so we'll just call this value here to be psi, like that. And then we could just do the integral, which is going to be negative, oh sorry, there's no more integral because we have done the integral. It's negative cosine omega t plus 2 pi over lambda sine theta A plus cosine omega t. Now this will be simplified much more further into EP over psi, negative cosine omega t plus psi plus cosine omega t. Now, what we could do is that we could just combine them both together. So if you know about the property cosine omega t minus cosine, sorry, it's cosine A minus cosine B, it's gonna be negative 2 sine A plus B over 2 and sine A minus B over 2. So if we plug this in, it's gonna be EP over psi to be 2 times sine A plus B, which is omega t plus psi over 2, and sine of psi over 2. So simplify this much more further, you would get EP over psi over 2 is going to be sine psi over 2. Multiply this by something which is dependent on t. So this is going to be your average electric field, which is going to be this. So this is the average electric field. So you would have this component here, which you call as the sine c normally, sine psi over 2. So now you could actually use this to compute the intensity. It's going to be S0 sine psi over 2 over psi over 2 squared. Now this pattern here is going to look something like this. It's going to grow up and then it's going to turn to be something like this. So this is the pattern that you would see if you're doing diffraction. You would have a center peak and then there are small peaks going to the side, depending on the wavelength. So because of this, there is something interesting when you are starting to talk about the double slit experiment, because there is this non-negligible width here. The pattern is going to be, it is going to be a combination of both the diffraction pattern as well as the interference pattern. So what you could have is that there are some peaks that are much more denser while others are not. So something like this. It's not a perfect sketch, but you could get the idea that there are these interference pattern as well as the diffraction pattern. So because of this, we will notice that if you have a very small hole for you to look at the object, you could have something which you call as diffraction. So let's say if there's two objects very close to each other, what might end up is that you would see something like this because of the property of the wave. Now, because of this, we need to find a way for us to quantify such minimum value for the two objects to be separated. And this is what you call as the Rayleigh criterion. So the way that we'll actually describe about this is by using the same idea as before. If we set one of the interference pattern to be at 0 and then the other one is at the max, it's going to look like the max is going to be on itself and then the other one to be on itself. So that condition is going to be, so sine theta was lambda over a, in which it's something that you know. So this pretty much comes from the condition of the destructive interference. And so if you take theta to be very small, theta going to 0, theta min is going to be, sorry, if theta is far smaller than 1, the theta minimum is going to be lambda over a. And this is your Rayleigh criterion. So a corresponds to the size of your hole, and then lambda corresponds to the wavelength that it produces, or the thing that you're seeing. And so this is where there is a limit in which how could you differentiate between two different particles. So because what we observe is normally around 400 to 700 nanometers, or 400 nanometers is pretty much almost blue or purple. So anything higher than purple, no, sorry. So anything that we use for us to obtain information other than the color purple is going to be much more blurry. You couldn't determine fine features, and this is why you use X-ray, you use UV for you to read off information of a very small object, something like the atom, like the very small structures of a bug's eye. You normally use X-ray or maybe even electron microscopy for you to obtain information about how those things look like. But anyways, the talk about electron microscopy is a very quantum mechanical way of observing such objects. So I will just leave that later on to see what is the relation between the electrons as well as the waves. But anyways, this theta min equals to lambda over a only works if you're talking about a slit. But if you're talking about a circular aperture, it's instead going to be 1.22 times lambda over the diameter of the aperture. So this 1.22 comes from the Basel function. And this 1.22 is something that I won't really compute in here. So if you are interested in the discussion of the Basel function, you could just leave it in the comment for me to discuss in a much more deeper manner. And so that's all for today's video. So this is where I will leave optics, and we'll later discuss much more in relativity and maybe even modern physics going forward. So thank you very much for watching, and please consider liking and subscribing, and also please share this to your friends who really need to understand physics in a much more deeper understanding. So thank you very much for watching, and I will see you on the next video.